Good morning. Welcome to Krishna's classroom. Let us continue with our exploration of the path from Riemann to Lebesgue. We have already introduced the ingredients required to define the integral. Now they are, of course, we started with R. Then on R, we define what are called the measurable sets. And then we had, of course, the consequence was we had the measure space, or rather measurable space. Now we introduced the concept of, from the concept of length for intervals, we extended that to over a class of subsets of R, larger collection of sets in R, and this we call the measure. So we had the introduction of measure. So we had the measure space. We had the measure space R, A. Then of course we introduce what are called measurable functions. Measurable functions on R, possibly extended real value, possibly. The measurability condition was that for a given f, the extended that means we are talking about the extended real valued functions, E measurable, E belonging to A, so that it is measurable, and such that F inverse of any open interval or F inverse of any open set is measurable. I mean, is a subset of, is a element of the class of measurable sets, and this is of course contained in E. So that is the domain of the function. Okay, this is measurability. In fact, there are various formulations of measurability, which you can, equivalent formulations, which we have mentioned at that stage, but that is immaterial. So now we have come to the stage how to define the integral. we have some experience of doing it with Riemann integral. And the problem was that the class of functions we could, for which the Riemann integrability was valid, were not sufficiently large to get a complete L1 space out of them. That was the problem. That's why we went through all these exercises, reworked the whole thing. Now, how to define the integral? This is the problem. So this is the main part. Answer. This we do in 3 stages. First stage, we work on what are called bounded measurable functions on a set of finite measures. Bounded on a set of this is the first stage. You will see, we will explore this in detail in our lecture, because this includes, in fact, all the Riemann integral functions. Okay. Now the second part is a measurable non-negative function on a measurable set E with a support of finite measure. Here what we do is, see, here we have developed it only on functions defined on a set of finite measure. Here what we do is, we are no more insisting that the function is defined on a set of finite measure. Okay, could be the whole of R. So it's a clear departure from what we could do on Riemann integral, because you recall the functions we were considering were bounded functions, bounded real valued functions defined on a bounded interval. Okay. So here we are going far beyond that. First of all, we relax the condition. Even from this, we are no more insisting that the function should be bounded. We are no more insisting that it is defined only on a set of finite measures. It may be defined everywhere, but with some restrictions on this. Okay. So we take only non-negative functions at this stage. Here we are not insisting that the function is non-negative, but here we work only on non-negative functions. So from this stage, we make an advancement, but now restrict to non-negative functions. The third stage is the general Lebesgue. Here the strategy is, of course, see, use 1 to define the Lebesgue integral for class 2. Now use 2 to define the integral of a more general class of functions. Here we are dropping the condition that of non-negative. Okay. How we overcome this is we take f to be measurable. This we can write as f plus minus f minus. This we have seen earlier, where f plus and f minus are both non-negative. I will go to the details later. Non-negative, and f is written as a sum of f plus and f minus. Now we define the integral if it is possible. If possible, we will define the integral of f to be integral of natural way. But this needs some kind of conditions. Of course, conditional. We shall explore the conditions in this. That is the strategy. Okay. So at each stage you see that this is the broad strategy that in solving any problem in mathematics. Okay. Any problem in mathematics, the broad strategy of attack on that problem is to reduce the problem to something we already know. Something we already know. That is the important part. Okay. And once we do that, use that knowledge to move further to the more general case. Okay. So these are 3 stages. The first stage is we deal with bounded measurable functions on a set of finite measures. Okay. In fact, our Riemann integrable functions would fall into this class. Okay. So all Riemann integrable functions fall into this class, and for all those functions, the Riemann integral would coincide with the Lebesgue. Last we shall see how we learn this. The second stage, measurable non-negative function. Now we put an extra condition that the functions are non-negative, and for which, and also another condition, namely that the support of it has a support of finite measure. Then the third one will be for general extended real valued functions defined on the measurable, on a measurable subset of R. The subset may be bounded or unbounded. It is immaterial, but there are conditions. I mean, they are all going to be there are going to be conditions for various things. And then we exploit the fact that such functions can be written as the difference of 2 non-negative functions. and then we apply the section 2 wherever it can be applied. Okay, and use this formula if that is possible. Okay, now we will say that's why I set conditional here. So we will explore these conditions. What are the conditions? It's not that all the extended real valued functions on R are Lebesgue integrable. No, that is not. But there is a subclass. There is a subclass which is bigger than what we have already considered, for which an integration theory is possible. Okay, so that is the third strategy. So once we do this, our task of developing the integral is over. Then we go for the consequences. The remaining steps are, how does this give you what is the form of the fundamental theorem of calculus in this case? That means we are now trying to link with the first notion of integral as antiderivative. So is it possible to link this with the concept of antiderivative? Okay, no, it's not going to be a free ride, but certainly we'll have to be careful here what kind of functions are for which this is true, or is there any such form. In fact, we get a fairly neat, nice relation between the derivative of the function and the integral of the derivative, or the given function and the integral of the derivative in this case, and that's very interesting. Okay, so once you do that, the next task is, of course, whether we achieve our objective or not. In fact, we achieve far more than asked for. In fact, it's not only L1 that is complete, but LP is complete for all P less than in this strategy, that is 1 less than or equal to P. All these spaces become complete spaces. So in fact, we meet more than what we are, or we get more than what we ask for. In this case. Okay, so that gives out our paths to the developing the Lebesgue integral. Okay. Now let me start exploring the first part. I do this a bit in some detail, because rather than just writing down the various theorems, I just do it in some more detail, because to get the feeling for what Lebesgue integral is, or how things keep working here. Okay, so let us do that, and that's very interesting, in fact. So that's our first task. So in this talk, primarily we will be dealing with the first case, and the other two we consider in our next lecture, and then maybe a couple of lectures more to make to show that our objective. Okay, so let us start with this. So we start with a bounded measurable function on a set of finite measures. So E is the E measurable that is E is a element of the measurable class of sets and measure of now F is a real valued function such that there exists M positive with mod F less than 1. For every x. So these are the two conditions that we have. These are the conditions. First of all, E is a measurable set, finite measure. F is a real valued function which is bounded on E. Okay. Now, how do we handle the integral of this? Okay. So, what one does is this. So, you see, this is the pictorial representation. I would put it this way because not assuming the function is don't be carried away by what I do because I am taking here E as a bounded interval, but that is not the case. So we are okay. So what one has is that this is bounded above and bounded below. So there is an M such that this is minus M. This is the graph of the function is over here, but remember, don't get carried away completely by the picture or the diagram because I have taken the interval, taken E as an interval, but that is not the case. That need not be the case. Okay, so E need not be N. So between M minus M and plus M. Now, what is the strategy that we use? We partition okay, so these are the bounds that minus M dx x. Now you see that we partition the interval minus M to plus M. to intervals. By choosing such that this is what you have. We have minus m Remember, we are partitioning the range of the function. So this is y0, y1, this is y1. That's a partition. Now we try to work out the pullback of this function. Now the pullback of this function is this. Pullback of this interval through this function is the following set. So this is the pullback. Okay, so let me write down. So we write by EI, we define F inverse of yi, the interval yi minus 1 to yi. That means the pullback of this, that means the set of all points which gets mapped by this function into this. So you see that this is the property. It's mapped. Okay. That's a property for I equal to minus 1 and En why? Then you see that we have EI these are all measurable sets. I mean, these sets are all measurable because you see that this is the pullback or by a measurable function of an interval and therefore it is measurable. So all EIs are measurable. That means EIs so we can talk about the measure of that. Okay. And you also have this property that they are mutually disjoint. Right? So this is your EI. This is your EI. EI need not be an interval, it depends on the function. Now we define, what we do is, we take the cutout of f on this set. Okay. Take the cutout of this function on this set. Hence I have marked this with yellow color. Okay, so what is it? Let defined as yeah, this is equal to f into chi, the characteristic function of E. Then yi minus 1 times chi I and yi times ei are lower and upper approximations of Fi by constant functions. On here. It's really fast. See how these things develop. So what we have is this. Phi this is the inequality that we get. Now you see you are working on constant functions. So if you have on a set a constant, suppose this is yi, suppose you have got this is yi, this is yi, then the area enclosed here is actually yi into measure of pi. Okay, so what you have, therefore you see that yi minus 1 to pi in fact I can put here E because Fi lives only on here. This is less than or equal to that's how we approximate it. This is yi and this is so the area enclosed between this portion of functions and this is going to be yi. This is yi. So yi minus 1, this is 1. So you have this inequality. So this area, okay, is this one. Okay. Therefore, you get this inequality, and what you have is this, that you see that sigma yi minus 1 chi ei is less than or equal to what is called, right, this is area of, which if you want you can write this as integral, if at all such an integral exists, we don't know. Sigma, oh sorry, this is f, simply f, approximate, right, I equal to 1 to n yi. So what do I do? What is that I have done? What I have done is I have approximated x from below and from above by functions which take only finitely many values. Okay? A lower bound and an upper bound for f by functions which take only many values. That's what we have done here. Okay, that is, we have, so call this, so let us write phi I or phi, okay, phi understand these functions. Phi takes only values y0, y1, y2, etc., yn minus 1. N values. Psi takes y1, y2, y. So this is squeezed between two such functions which take only finitely many values. And for those finitely many values, we can define the integral. Okay. So these are what are called simple fractions. Shall make a definition of this later. So we have y less than or equal to, it's squeezed between two simple fractions. Now we have for we can define the integral is naturally sigma equal to 1 to n y I minus 1 times share of ei and yi share of e. Okay. Naturally, the geometry tells is between and they are sensible. So what we have is this. If at all, this is of course Krishna. Does this make any sense? Oh, so you have to say what when it makes sense. We have to now say when it makes sense. What is the strategy? The strategy is to refine this partition by introducing more points. Okay. So we refine it. What happens when you refine it? See, if If phi dash is a refinement of phi and psi dash is a refinement of we have if it is meaningful. This is what happens. Exactly as we had in the case of Riemann. We had the lower sum and upper sum, and then the lower sums are all bounded above and the upper sums are all bounded below. Okay. So the strategy is now pretty clear. Okay. So what we have is this. Okay. So we called those functions what are called the simple functions. Okay. Be the collection of all such simple functions such that simple functions so we now define the upper integral and the lower. Upper and lower integrals of f. What is that? So we define this integral over infimum over psi where psi of course is simple SNOE. Now this is called the upper integral, and the lower integral is upper integral, the lower integral is supremum there are simple functions. These are well defined. Okay, so you see that that follows from the properties of the real number system, because the supremum and infimum exists. So what we have is this. So we have integral over these two x's. This we don't know. We say that or f is Lebesgue integral. If these two are equal, then we say the function is Lebesgue. Now the question that you ask is, which bounded measurable defined on on sure, R integral. That's a question that we take up at this stage. That's quite very easy to see. See, I am not too rigorous in my thing, but I am just indicating the path that follow, and then you have to write a very rigorous proof, giving all sorts of arguments support. Okay, but this is available in earlier lectures, giving very elaborate discussion. So this is the question that you are asking: is this integrable? Okay. Now we claim that we have the following: all Lebesgue measurable functions real value bounded functions on a measurable set with finite measure of the answer. I am not giving the details of the proof, but the answer is very simple. Okay. Choose the partition. Thus we have done it. Okay. Such that mod such that for a given epsilon positive, mod now this is possible because you have to just divide a length of 2m into finitely many sets. Each interval is of length less than epsilon divided by epsilon of e. As epsilon becomes smaller and smaller, the number of divisions will, but still it will remain finite. Okay. Then we make the observation. Then what we have is integral over phi is equal to sigma yi minus 1 I equal to 1 to n. Now you see that integral over pressure of, and this is of course less than or equal to, this is non-negative, epsilon sigma each one is less than epsilon divided by me, and this is less than or equal to because EI is contained in. Okay. Therefore, you see that going to the definition, we have integral over you see that the difference between these two is squeezed between these two, and you know that the difference between them is less than epsilon. Therefore, you can make the difference between these two integrals as small as you, as small as you want. Therefore, you can get integral as small as you want, and for every epsilon. That means they are equal. So all bounded measurable functions defined on sets of finite measure are Lebesgue integral. Now, one remark that you have is all Riemann integrable functions. What are the Riemann integrable functions that we have? We have insisted on the function is defined on a bounded interval and the function itself is bounded. Okay. So, look at this remark. For so Riemann integrable RAB is a subcollection of this. This is what you have. We have seen that if the discontinuity is too large or the set of discontinuity is too big, then we will have to, the function is not Riemann. But here you see that no such thing happens. Because if you take E to be see, the point is this. See, we are taking supremum and infimum over over what are called simple functions. We are doing the same thing in Riemann integral, but on a restricted class of simple. So the difference is this. A special kind. What is that? Namely, they are defined on intervals, not because you see that all intervals are so they are functions of this type. F I E I. These are the simple functions that is where EIs are intervals. Subintervals may be. Whereas this is for Riemann integral. For Lebesgue integral, we consider f chi I EIs are subintervals, EIs are measurable subsets of E. Okay. It's a larger class on which we are taking the infimum and supremum. Therefore, the the supremum and infimum are calculated over a larger class of functions, and that's a very, very significant difference. Okay, so we get a better edge and we get a reach to many more functions than Riemann integral functions. Now, for many that is the reason. Okay, because we take infimum and supremum over suppose you take E to be an interval. Now, for Riemann integrability, we consider only what are called steps. That means they are defined only on intervals, taking finite values on intervals. So here we are taking finite on measurable sets. So it's a larger collection. So you get a far more incisive. That is how you get more class of functions now integrally. And this is what enables us probably to address the completeness problem. That means you have a larger class of Riemann integral or Lebesgue integrable now than the Riemann integral. Or in fact, we can say that this is true. We get the Riemann integrable function from AB is contained in Lebesgue integrable functions on E is in this case first of all, it is defined only for intervals, bounded functions on intervals. Here it is defined on any measurable subset of R with finite measure. Okay, so we have covered a lot of ground now, but we have throughout kept the functions to be bounded on this because we didn't want to do any adventure. So we wanted to go beyond this, but we will do it systematically. And this is how the idea works. So what have we done? Instead of subdividing the domain, subdivided the range, got the pullback. The pullback were all measurable sets because we are taking only measurable sets. And you see that all Riemann integrable functions have this formula. Okay. And in this case, we also get the Lebesgue integral of f is the same as the Riemann integral. That's interesting. So it's a genuine extension of the concept of Riemann integration with a far deeper reach than we had. And we have the so Lebesgue integration is a genuine extension of but that's the most exciting. See how the whole idea has come up. Now I think it was pretty clear how we get the incisive reach out to a larger class of functions. So that's a very interesting thought. I think I'll take up the next two stages, mainly the two steps we were talking about. How do we go from here to a larger class of functions? Okay. So those extensions I'll take next week. So I thought that I would do this because this is free from the proofs, disturbances of the proofs. So maybe you go through these 6-7 lectures, which introduces abstract integration theory, and then see the 80 lectures on Lebesgue integration theory. Easier, and all the details of the proof. Okay. Thank you very much.